Hello everyone, I am going to talk about ultrasound today. This is module number 15 of PG Pathshala, paper 6 of radiation biophysics. I am Dr. A.K. Shrivastava from University College of Medical Sciences and Guru Tegh Bahadur Hospital, Delhi. I am going to talk about ultrasound. The introduction of ultrasound is that sound having frequency more than 20 kilohertz is called ultrasound. Ultrasound imaging uses very high frequency, usually 1 megahertz to 7.5 megahertz sound waves to create an image of organs and structures present inside the body in a real-time fashion. Objective of this module is to explain the properties of ultrasound waves. We will describe what is the decibel notation, explain ultrasound reflection, refraction and scattering, characterize ultrasound transducer and describe the property of ultrasound transducer, describe different modes of ultrasound display. So as I said, ultrasound waves are those sound waves having frequency more than 20 kilohertz. Our audible range of frequency is 20 hertz to 20 kilohertz. We will see the first is the ultrasound physics. Basic parameters in ultrasound physics is wavelength, the space between two consecutive compression or two consecutive REFRACTIon, as in this figure, is called wavelength. The frequency is the number of oscillations per unit time is called frequency. Time period, the time taken for one complete oscillation in the density of the medium is called the time period of sound wave. The amplitude is the magnitude of maximum displacement in the medium on either side of the mean value is called amplitude of the wave. Now the velocity of sound wave, it depends on compressibility of the medium and the density of the medium. Normally, largely speaking, it depends on the compressibility of the medium. The velocity of sound wave is universally proportional to compressibility of the conductive medium. For example, the bone is less compressible and the velocity of bone is very high. Velocity of let us say for air, it is very highly compressible and therefore velocity of sound wave in air is much less as compared to the bone. The velocity of sound wave in soft tissue is 1540 feet meter per second. Coming to the relative sound intensity, this is measured in decibel, which is equal to log 10 relative intensity of I1 upon I2, which is the I1 is the original intensity, I2 is the intensity of returning echo. Taking log of it tells you about 10 of this log of this ratio. It tells you about the intensity, relative intensity of sound wave. The intensity of sound wave is longitudinally along the length of the beam. The beam acts as a parallel bundles for a certain distance beyond which it disperses. The parallel component is called near zone or Fresnel zone. The divergent portion of sound wave is called, beyond certain limit, is called Fresnel zone. In this figure you can see here the near field or near zone is called Fresnel zone, and the this is beyond this one, beyond the Fresnel zone is called Fraunhofer zone. The length of Fresnel zone is equal to r square, that is the length of Fresnel zones, r square upon 4 lambda. 4 lambda is the wavelength, 4 of lambda, 4 times of lambda. The Fresnel zone is longest with a large transducer and high frequency sound wave. Fresnel zone is shortest with a small transducer and low frequency sound wave. Now coming to the interaction of ultrasound waves with the tissues. When ultrasound interacts with the body tissues, it has the reflection, refraction, absorption. The reflection is the image is produced by, in fact this produced by the reflected portion as shown in the figure. When a sound beam interacts with the body tissues, a percentage of beam reflected back towards the transducer, which is the production of sound waves. It depends on the tissue acoustic impedance, the beam angle of the incidence. The acoustic impedance is the product of density and velocity of the sound wave. So we can say that density in a particular medium, the velocity is same, and therefore it largely depends on the density of the material. So as sound wave passes from one tissue to another tissue, the amount of reflection is determined by difference in the acoustic impedance of the two tissues. As sound wave passes from one tissue plane to another, the amount of reflection is determined by the difference in acoustic impedance between two tissues. Greater the difference, greater percentage of reflection. As you can see in this figure, the percentage reflection is sound wave is coming over here, and a portion of sound wave is back reflected, which is called echo. Now angle of incidence, as in this figure, the higher the angle of incidence, the less amount of reflected sound waves. So this angle should be less than 3 degrees. As sound wave passes from one tissue plane to another, the amount of reflection is determined by difference in acoustic impedance between two tissues. As shown in the figure, the percentage reflection is equal to Z2 minus Z1 upon Z2 plus Z1 whole square into 100. This is valid when sound wave is exactly perpendicular to the surface. R is the percentage of reflected beam, Z1 is the acoustic impedance of medium 1, Z2 is the acoustic impedance of medium 2. So as you can see here in this figure, the percentage reflection is Z2 minus Z1 square upon Z2 plus Z1 square into 100. Now coming to the type of reflectors, there are two types of reflector. One is the diffuse reflector, second specular reflector, second is the diffuse reflector. The specular reflector reflects the sound beam very efficiently in a defined direction. For example, a diaphragm as shown in the figure 5 which produces higher amplitude of echo. But the condition for a specular reflector is that the surface of tissue must be smooth, size of the tissue is more than the wavelength of ultrasound wave. So those tissues which fulfills this condition are called a specular reflector. Now diffuse reflector, as you can see in this figure, it reflects the ultrasound beam in all the direction. This produces low amplitude echo. A condition for diffuse reflector is as shown in the figure. The tissue surface is not continuous and the size of tissue is much less than the wavelength of ultrasound wave. So that means most of the waves are scattered, and the intensity of therefore reflected echo is much less. Next is the refraction. This is the bending of wave as they pass from one medium to another medium, as shown in figure. You can see here a percentage of wave is refracted. It deviates from its original path. Therefore, when sound beam passes from one medium to another medium, its frequency remains constant, but its amplitude changes to accommodate a new velocity in the sound medium. The refraction causes artifacts. We call it as refraction artifact, which might lead to spatial distortion. Next type of interaction is absorption. It refers to the conversion of a sound energy to the thermal energy. The factors which determines the amount of absorption is the viscosity of conducting medium. Ultrasound wave is directly proportional to viscosity of the conducting medium. Higher the viscous liquid, less is the attenuation. Second is the relaxation time of the medium. This increases relaxation time, increase in the absorption of sound wave. Third one is the frequency of sound wave. So higher the frequency, more is the absorption. So higher a viscous liquid, more absorption. Higher relaxation time, more absorption. Higher frequency, more absorption. And therefore attenuation, it refers to the total propagational loss of beam or sound beam, including absorption, scattering, reflection, refraction. This loss of intensity is known as is represented in a decibel, and it is minus a negative value. Attenuation coefficient is usually 1 megahertz per centimeter per 1 decibel per megahertz per centimeter, wherein the frequency f is the frequency, x is the path length, and this is called attenuation coefficient of the material. Now coming to the transducer. Transducer is a device that converts one form of energy into another form, as shown in figure. The ultrasound transducers are used to convert an electrical signal into ultrasound energy, and also converts ultrasound energy back from tissue into electrical signal. The component of an ultrasound transducer is the piezoelectric crystal. Lead zirconate titanate crystal is the heart of the transducer. It is about 0.5 millimeter thick. Piezoelectric crystal element created near the face of a transducer. The front and back of the crystal are coated with a thin conducting film to ensure good contact with the two electrodes that will supply the electrical field that is used to oscillate the piezoelectric crystal. The outside electrode is grounded to protect the patient from any electrical shock. The inside electrode is thick against the thick backing layer that absorbs the sound waves transmitted back into the transducer. An acoustic insulator of rubber or cork prevents the sound from passing into the housing. The housing is usually a strong plastic. The backing block or backing layer, this layer is generally made up of tungsten and rubber powder embedded in a epoxy resin. Matching layer, the mixture of aluminum powder of resin epoxy used for energy transfer, efficient energy transfer between the transducer and the patient. The thickness of matching layer is a quarter of the wavelength of sound wave in the matching layer. As you can see here, this is the diagram of structure of transducer. Now coming to the piezoelectric effect. When an electric voltage is applied to these crystal, they change the shape rapidly. The rapid shape changes or vibration of crystal produce high frequency sound waves, as you can see here. Conversely, when the sound wave hit the crystal, they emit electrical signal back. So you can see here the now the type of transducer. There are mainly two type of transducer. One is the mechanical transducer, other one is the electronic transducer. Mechanical or oscillating transducer type, oscillating transducer, enclosed and rotating wheel transducer. Electronic transducer are also called real time electronic transducers or linear transducer, phased array transducer and annular array transducer. Now coming to the mechanical transducer. Mechanical transducer have both steering and focusing of beam is mechanical here, as you can see here. This is the now in first type of it is the oscillating transducer, unenclosed crystal. A single crystal transducer crystal is used for oscillating through an angle. A sector shape image is produced by this one. Angle of oscillating transducer can be varied from about 15 degree to about 60 degree. Here the frame rate are generally about 15 to 30 seconds, as you can see here in this figure showing oscillating type of transducer. Another oscillating type of transducer is that here the crystal is transducer is enclosed in a crystal. In this type of sector scanner, the transducer is enclosed in a castor water filled with container. Castor oil is commonly used as a fluid. If the transducer is mounted near the surface, a sector shape is produced. When the transducer is mounted several centimeters behind the front surface, trapezoid image is produced. So you can have both sector and trapezoidal image, as you can see here in this figure. This is showing oscillating type of transducer. Another type of mechanical transducer is a rotating wheel transducer. It contains 3 or 4 transducer piezoelectric element enclosed in an enclosure. There are about 120 degree to 90 degree apart of a wheel. The motor rotates the wheel at a constant rate in one direction only. Only the transducer, the crystal that is behind the acoustic window is allowed to trapezoid shape image may be produced, as you can see here showing rotating wheel type of mechanical transducer. Now coming to the electronic transducer, as you can see here, this electronic transducer can have linear array. This consists of number of small rectangular shaped transducer element arranged in a line. Transducer array is composed of about 128 to 256 small piezoelectric elements arranged in a line of say about 12 centimeter. Decreased transducer size, shorter Fresnel zone and increase the angle of dispersion problems solved by using an array with a mini narrow transducer element to produce high line density. By firing the transducer in a groups, causing group to act as a single transducer, and therefore length of near field is preserved. At the same time, it can have a large amount of scan lines. Coming to the phased array or steered array transducer, it usually composed of about 64 to 128 individual elements in a smaller package. But here all transducer elements are activated simultaneously with a slight time gap to produce a single transducer beam. By using a time delay in the electrical activation of discrete element across the face of transducer, the ultrasound beam can be steered and focused electronically without physically moving the transducer on the patient. This phased array transducer is helpful in cardiac imaging, as you can see here in figure. Now another type of transducer is called annular array transducer. Here each element has the shape of an annular ring and multiple elements are arranged in concentric rings about a central transducer element. Beam focusing are achieved electronically. So this you can see here in this figure, annular array transducer. Here it forms an annular shape, and therefore some artifact like slice selection artifacts can be reduced by using annular array transducer. Now coming to the display modes in ultrasound, there are A mode, amplitude mode, B brightness mode, TM mode is the time motion mode. A mode, which stands for amplitude mode. As you can see here in the A mode, and in this figure, in A mode echoes are displayed as a spikes projecting from a baseline. The baseline identified the central axis of the beam. The height of the spike is proportional to intensity of returning echo, with a strong echo producing large spike. When a voltage pulse strikes a transducer, an echo spike is generated on the monitor to mark the beginning of sonic pulse. In the A mode, the display on cathode ray tube contains information about the depth of structure and the amplitude of the returning echo. It is basically used in ophthalmology and echocardiography. Now coming to the B mode. As you can see here in this figure, B stands for brightness mode. The B mode produces a picture of a slice of tissue. Here the echoes are displayed as a dots. The dot depends on the amplitude of returning echo. In the B mode scanning techniques, the transducer is placed on the patient skin with the mineral oil on the skin acting and to ensure that good acoustic coupling between transducer and skin. This is called contact scan. The transducer is moved across the body while it is being rotated, producing a compound contact scan known as P scan, whereas I told you brightness mode, wherein brightness of dot represents the intensity of returning echo. Now next type of display is TM mode. As you can see here in this motion, time motion mode, the spikes are represented as a dot displayed along a vertical baseline, and the location of dot is an indicator of the depth. The brightness of dot is proportional to strength of returning echo. The horizontal line baseline is an indicator of time. This type of TM mode is used in cardiac examination, as you can see here in figure. Now coming to the Doppler imaging. This Doppler imaging is based on Doppler physics, Doppler principle. Doppler is a change in the perceived frequency of sound emitted by a moving source. If the direction of motion of target is towards the transducer, an increase in the frequency is observed, and if the direction of motion is away from the transducer or source of a sound beam, a decrease in frequency is observed, as you can see here. So Doppler shift frequency is equal to 2 into frequency into v cos theta upon velocity of sound wave. As in this figure you can see the Doppler shift frequency is displayed by this formula. The Doppler shift depends on the angle between sound beam and the direction of blood flow. If the angle is equal to 0, then Doppler shift is maximum, because cos theta is 1, cos 0 is 1. It depends on the frequency of initial beam. At frequency between 2 to 10 megahertz, Doppler shift falls in the audible range of frequency, audible range of sound waves, and therefore we can record this Doppler shift, we can hear this Doppler shift. The types of transducer Doppler technique is known as continuous wave Doppler, pulse wave Doppler, duplex scanner, and duplex color flow imaging, and of course power Doppler. Continuous wave Doppler, this mode employs two piezoelectric elements, both contained in a single crystal. One crystal transmits continuous sonic signals at the known frequency, and other piezoelectric element receives the returning echo and records their frequency. The difference in frequency or Doppler shift usually falls in the audible range, as I told you earlier, and after amplification constitute the Doppler signal. Advantage of continuous wave Doppler is that here instrumentation is very simple and inexpensive, good quality, low noise signals, but the disadvantage is that continuous wave Doppler lacks any form of depth information about the tissue being isolated. Second is that no time gain compensation. Coming to the pulse wave Doppler, it provides the mean for detecting the depth at which a returning signal has originated. The depth can be positioned via cursor at any point along the axis of the pulse Doppler beam. To determine the Doppler shift at a specific depth requires that ultrasound transducer produce a very short duration burst at a precise rate of repetition, known as pulse repetition frequency, which determines the maximum depth from which a Doppler shift can be detected. The advantage of pulse wave Doppler is that it can identify the source to the signal. Blood flow signal can be obtained from a range gate, but the disadvantage is that quality of pulse wave Doppler signal may be suffer from background noise caused by switching circuit between receiver mode and transmitter mode, and we have a problem of aliasing which is called Nyquist limit, and this aliasing may produce a kind of artifacts in the image. Coming to the duplex scanner, some Doppler equipment combines a real-time imaging mode such that the vessels on the structure of interest can be selected. Duplex Doppler is a single gated pulse wave Doppler. The advantage of duplex Doppler is that site of Doppler examination can be missed because it combines the real-time ultrasound with the Doppler sound, and the size of sample volume can be chosen. Beam vessels angle can be measured very accurately within 2 to 3 seconds. But disadvantage of duplex Doppler is that here the beam angle may be restricted. Blood flow information is obtained from only one side in the image. Now coming to the Doppler color flow imaging, this is the very popular type of color flow imaging Doppler. This color flow imaging Doppler has been developed to produce imaging of blood flow out an entire real-time image, allowing visualization of blood vessels and their flow characterization, plus image of the surrounding tissues which are not moving. A multi-gated system can be combined real-time transducer, a real-time system to obtain Doppler signal across an entire US image, ultrasound image. This is the principle of color flow Doppler imaging. Color flow imaging requires that ultrasound beam remains stationary at one point of time for a brief period of time to move to the next line and so on. The electronic transducer may steer the beam. Color Doppler presents a real-time image of both anatomy and picture of blood flow, gives the Doppler information. The advantage of color flow Doppler is that the technical efficiency, global Doppler sampling, flow throughout entire lumen scene because of localization of abnormalities better, improved definition of lumen, rapid acquisition of data. But disadvantage of color flow is that it computes the mean rather than the maximum velocity at each point. That is number one point, disadvantage. And another disadvantage is that PRF is limiting the Doppler shift frequency that can be detected. It is angle dependent flow information, and moreover it has a high cost. Now there is another type of imaging which is combined with the color flow imaging, is power Doppler, wherein the pixel intensity is displayed in the form of amplitude of echoes. So number of echoes are represented with a single color, which is called power Doppler, whereas in color flow imaging you can see both the colors moving away from the transducer or moving towards the transducer. Those blood which are moving towards the transducer will be displayed with a various shades of red color. On the other hand, those bloods which are moving away from the transducer are represented with the blue shades of blue color, different shades of blue color. So you can see this is represented in the form of color, and this is why it is called color flow imaging. But sensitivity of color flow imaging is comparatively smaller, because it is less sensitive to very smaller vessels. Very small vessels may not be visible, may not be isolated. So we can use the color amplitude imaging, which we call it as power Doppler. So with the aid of color flow imaging and color flow Doppler, we can use a great deal of information about the blood flow. To summarize this module, first of all, as I told you, ultrasound is the sound beam having frequency more than 20 kilohertz. Any sound wave having 20 kilohertz, more than 20 kilohertz are known as sound wave, and in ultrasound imaging 1 to about 7.5 megahertz transducers are mainly used. In fact, for cardiac ultrasound, cardiovascular ultrasound, it may be about 20 megahertz or so, or even higher. When ultrasound beam passes through patient body, it gets attenuated, its intensity is reduced. This process is known as attenuation. This attenuation is occurring due to reflection, refraction, and scattering and absorption, of course absorption. So this absorption, reflection, and refraction causes the attenuation itself in the ultrasound beam. When ultrasound beam interacts with the body tissues, in fact portion of ultrasound beam is reflected in the form of echo, and these echoes are utilized to reconstruct the image in ultrasonography. The transducer is the device which produces ultrasound waves and detects the ultrasound wave. At first it acts as a transmitter, wherein the electrical pulses are converted into ultrasound pulses, and these ultrasound pulses are sent out into the patient, and when ultrasound waves interacts with the body tissues, a portion get reflected in the form of echoes, and these echoes are detected or received by receiver, which converts these ultrasound pulses into electrical pulse again. So this is the structure of transducer is that main heart of the transducer is a piezoelectric element, usually lead zirconate titanate, PZT. That is the heart of the piezoelectric ultrasound transducer. And in a structure of ultrasound wave, we have the piezoelectric element, we have the backing layer, we have the matching layer, coming to the modes of display, we have three modes of display of ultrasound beam. One is the amplitude mode, A mode. Second is the B mode or brightness mode, wherein ultrasound waves are displayed in the form of dots. Brightness of dot depends on the intensity of returning echo. Then we have the TM mode, wherein this brightness is moving with the time, that is basically used in cardiac imaging. The Doppler scanner, Doppler ultrasound uses Doppler principle, wherein the intensity of sound wave is perceived to be different from transmitted wave because of the motion of the structure. For example, this Doppler is useful in detecting the blood flow. Blood is moving. Doppler may not be used for a stationary structure, because in case of a stationary structure, the frequency of sound wave transmitted and reflected is same. There is no change in the frequency, wherein with the flowing blood there is a change in the frequency of transmitted and received waves, ultrasound waves, and this Doppler shift is utilized to get the information about the blood flow. There are 5 steps in the blood flow techniques. One is the continuous wave Doppler, we have the pulse wave Doppler, we have the duplex Doppler, we have the duplex color flow imaging Doppler, CFI color flow imaging, and the power Doppler. With this, we thank you very much. नाउ
ये अभी
मेरे ख्याल से इसमें समरी नहीं है।
11 मिनट ये है और 21 11 32 मिनट
हाँ
समरी
मेरे
एंड
ख्याल,
हो गया।
हाँ वही नहीं, इसी ने तो मैं
चलिए,
बोलता
इतना
गया,
में चल जाएगा।
मैं समरी बोल दे रहा हूँ।
लास्ट में समरी खुद से बोल देंगे।
हाँ हाँ कोई दिक्कत नहीं।
31 हो चुका है, 2-3 मिनट और बोल दो।
हाँ हाँ समरी में बोल दो, इसी ने तो मैं देख रहा था कि और कुछ है इसमें।
अच्छा, नहीं है सर।
हाँ हाँ ठीक है तो